Analog to digital converters, or ADCs, convert an analog voltage to a digital word. And remember, a digital word is effectively a combination of some number of bits. So let's define some terms. On the analog side, I'm interested in the kind of full-scale voltage range that I want to be able to convert. So I might have some minimum voltage and some maximum voltage, and the difference between those I'm going to define as my full-scale voltage range, or VFSR is going to be equal to Vmax minus Vmin. So on your Arduino, for example, you might have a full-scale range of 5 volts, where your max would be 5 volts and your min would be 0 volts. On the digital side, everything is defined by the number of bits in the ADC. So if I have m bits, that's ultimately going to give me 2 to the m codes or values that I have to represent that analog signal. And finally, going in between my analog to my digital world, I have my ADC. The ADC is going to have a clock signal that's going to determine my sampling time, my delta t minimum that I might have, or my sampling frequency maximum. So as we mentioned, that ADC is going from a voltage input to a binary output, or a code output. And in an ideal world, I have enough codes that I effectively have a one-to-one mapping between these two things. So that would be my ideal conversion, for example. In reality, it's a little different. In reality, your ADC will have a limited number of outputs based on the number of bits. So, for example, let's do something simple. We have 2 bits for my ADC. So to see the real conversion that I might have between voltage and my output code for a 2-bit ADC, let's label our axes. Let's say I have a 4 volt full-scale range for my ADC. So I have my 1 volt here, 2 volts here, and 3 volts here. And for 2 bits, I have 4 possible codes as output. I have 00, 01, 10, and 11. This actual conversion will depend a little bit on the type of ADC that I actually have. But let's say once I get to a half volt here, I jump up to 0, 1. So I'm at 0, 0 up to half a volt. I jump up to 0, 1, and then once I get to 1.5 volts, I jump again. And then once I get to 2.5 volts, I jump again. And so then 2.5 all the way up to 4 volts, I'll have that 1, code. So to write that a little bit differently, I have this mapping between my output code and my input voltage. So 0, 0 will give me between 0 and 0.5 volts, so I'll get a 0, 0 if I'm somewhere in here. If I'm at 0.4 volts, I'll get a 0, 0, for example. If I'm between 0.5 and 1.5 volts, I'll get a 0, 1 at the output of this particular ADC. Between 1.5 and 2.5, I'll get a 1, 0. Between 2.5 and 4 volts is a 1, 1. So you can see there are going to be a lot of interesting conversion errors that are going to creep in here, depending on how I divide up those spaces. So given this reality check, can we actually calculate what resulting code we might get for a particular input voltage to an ADC? So the way I'm going to do that is look at the fraction of voltage that I have on my input. So Vin divided by my full-scale range of voltage, and then this is times 2 to the m. So the total number of possible codes times the fraction of input voltage is going to give me my output code. And there are obviously a lot of rounding errors that are going to depend on the type of ADC that you have. And we're going to default to rounding down. So let's go through a quick example of this. On my Arduino, I have a full-scale range of 5 volts. I also have a 10-bit ADC, so M is 10, so I can go up to 1023. Let's say I have an input voltage of 2 volts from some particular sensor that I'm interested in measuring, And the corresponding code for that is going to be 2 volts divided by 5 volts, or 40% of my full scale range, times 2 to the 10. And this will give me 409.6. And I'm going to round down. Obviously, I don't have any decimal points, so I'm going to say my code is 409. Okay? And that depends, once again, on the type of ADC that I'm actually using and how it's actually going about at the transistor or integrated circuit level of actually computing these codes. So by the same token, I can calculate an approximate input voltage that I had on my ADC pin based on the code that I'm actually reading. So in this case, I'm looking at the fraction of my full value range, given my number of bits that code is, multiplying that by my full scale voltage range in order to get Vn. Now, if your full scale voltage range doesn't start at ground, which almost all of them do, you'll have to adjust this as well based on whatever your ground level is. So if I go back to that example that I had previously and take that code 409 that I just calculated and try to figure out what the approximate input voltage that I had on this pin was, I'm going to get 1.997 volts. Right, so this is 3 millivolts off of the kind of original 2 volts that I used for the first calculation, and whether that matters or not is going to depend on your application. So that's some of the quantization error that I'm seeing right here. So some of those conversions, as I mentioned earlier, depend on the type of ADC. So there are various ways to actually construct an analog to digital converter at an integrated circuit level. In fact, you can actually do this out of discrete components as well, especially with the slope ADC. The most common ones that you'll find on devices like microcontrollers are going to be slope ADCs or the SAR, or successive approximation register ADC. If you buy a discrete ADC chip, oftentimes you'll find sigma delta ADCs or flash ADCs as well. So slope ADCs and dual slope ADCs, which are a variation on slope ADCs, are generally going to be fairly simple to implement. So this is something that you can build out of discrete components. As a result, they're fairly inexpensive, but they're also very slow. Typically, you're looking at milliseconds or more per conversion of an analog voltage to a digital code. Also low resolution. So typically, you're going to find these in kind of the 6 to 8-bit range. They might go as high as 13 to 14-bit, but that would be pretty rare, more typically in around that 8-bit range. The successive approximation register, or SAR, or SAR ADC, is also incredibly common on microcontrollers like the one that is on your Arduino. They're a lot faster and can do up to 10 megasamples per second. They're also higher resolution, so typically they can go up to 18-bit resolution, although typically, once again, you'll more commonly find them in, say, the 12-bit resolution range. On a microcontroller, maybe down to 10-bit like you have on your Arduino. So sigma delta ADCs have the highest resolution. So if you're doing some really fancy audio sampling or something like that, you want very, very high resolution. So a lot of those horizontal lines, so you have these very small quanta, a lot of values that you can assign to your analog signal, you might want to use a sigma delta ADC for that. So typically you're looking at resolutions up to 24-bit for sigma delta ADC. And flash ADCs solve the other part of the problem. They're the fastest, up to 6 gigasamples per second. But typically they're limited to something like 8-bit resolution. So not very high resolution, but you can sample really fast. So this might be a really nice ADC to use in a sensor application or a measurement application where you need those really fast samples to detect very fast changes in your signal, for example. But all of these different types of ADCs, despite how they're implemented, are ultimately doing approximately the same thing. They're taking an analog voltage and converting that to a digital word. And how fast they do it And the number of bits that they have at their disposal for those resulting codes are going to depend very heavily on the type of ADC that you have available to you.